Greetings! My name is Roberto Valdez, Master of the Science of Geography and instructor at Northern New Mexico College in Española, New Mexico. I'm going to talk to you about systems theory. That is today's objective. Geography is a science involved with the description, distribution, and interaction of the physical and biological features on the Earth and in the atmosphere, as well as human activity with both of them. In today's lesson, we are going to discuss how systems theory works. There are two kinds: open and closed systems, feedback, and system change. And we're going to relate all of what we're going to learn to how the Earth works in its systems. First of all, we need to define theory. A theory is, well, some of you might say boring theory, but I can assure you that we need it because it colors the perception of how we look at the real world. It provides us statements, principles, and ideas that help us to rationally explain what we're seeing. Now, 500 years before Christ, the Greeks in ancient Greece were learning to question the contradictions that they were seeing in the superstitions that they believed in. They were developing what we call the rational mind, which is basically the ability to question contradictions. So they were developing early on the scientific method, which is illustrated on the flowchart at the right. First off, we start from the bottom. We have to, the premise of the scientific method is we have to prove something rationally. And we do it by first living in the real world and then making observations. And these observations lead to an educated guess about what it is that we're seeing. We use what we call inductive reasoning. We reason out that what we are seeing is explained this way, and we make this educated guess. And then this educated guess can be used to make a prediction. So that prediction sets the premise by which we can test something. And tests will validate whether the prediction we made is true and whether the hypothesis backing it up is true as well. Now, if there's something consistent that happens, go to the top of the flowchart shown here, you will see that it can become a theory. And that theory then feeds back downward in this flowchart, coloring our perception of the real world, whether it's something we saw on the ground not happening on the land or in the atmosphere, in the weather. We can now explain it. Now, let's say the test fails. Well, if it does, we have to modify it and then start the process all over again. That is, in a nutshell, the scientific method: proving something rationally and seeing and testing if it works. We're now going to relate the scientific method to how we look at how Earth works. It's called systems theory. It's the biophysical Earth, that is, life forms that live on Earth itself and in the atmosphere. So a system is basically a collection of parts. You might think of your own digestive system. You have your stomach, your liver, your pancreas, your intestines, and all the other unmentionables that I have not mentioned yet. They all are interrelated. They all work together. They're all chained together. So in this way, systems theory, you might understand a system is just an ordered, interrelated set of parts linked together by flows of energy and matter. And they work or are driven by some driving process. And a system is all these collection of parts that are distinct and kind of separate from the surrounding environment. In systems theory, we have to separate two different types. One is called the open system, which is linked to the environment outside of it in some way, drawing in energy or giving energy to it. And then there's a closed system in which it's all self-contained. Then there is positive feedback, and then there is negative feedback. So these are things to remember: open system, closed system, positive feedback, and negative feedback. Here are the details on those. We could probably say that Earth is a closed system. It's not a perfectly closed system, but it's pretty much by its atmosphere sealed off from outer space, and we get to enjoy life-giving elements on this planet. Closed systems are very rare, but they nevertheless have to be identified. They have no inputs and no outputs. So all of Earth is said to be a closed system with respect to physical matter. Now I know you can say, well, what about the meteorites that fall out of the sky? Okay, so that's a little bit right there. So it's not a perfectly closed system. But you could say also, well, hydrogen, it escapes out into space as well. So, but still, it is closed enough that, you yourself and me too are not floating out there in space. We're pretty much locked into this environment, in this globe we call planet Earth. Let's look at an open system by contrast, and you'll see why Earth is justifiably a closed system. By contrast to the planet Earth, we have trees, which grow and engage in what they call photosynthesis. It's how a plant makes food using the rays of the sun. Sunlight enter CO2, carbon dioxide, enters in, and the tree expires oxygen. It takes in water, and it transpires water. That is, it sweats out water into the atmosphere. Now, that's in the daytime. In the nighttime, you have the same processes going on, but you have another peculiar thing happening with the tree and its leaves. It produces a little bit of heat. Every living thing produces some heat. A tree, for example, in the winter, have you ever noticed that the snow will quickly melt around a tree or a set of plants quicker than in an open, empty ground field? This is the kind of thing that we see. A living, breathing thing does produce some limited heat, but it is part of an open system because it receives inputs and emits outputs. That's what makes it an open system. Now here's this other term that I want you to learn. It's called system feedback. System feedback is a regulatory system on the system itself. It keeps growth from going crazy and run away, and it keeps the thing from getting disrupted by this feedback loop. It experiences positive or negative feedbacks. That's what system feedback is, and I'm going to try to more perfectly illustrate that for you now. Another way to think of a system feedback or a feedback loop is encouragement and discouragement. So when you have a negative feedback, something is encouraging, or we could say discouraging, a response. It's encouraging a decreasing response. So if you don't give this plant water, it starts to dry up. That's called negative feedback. But if you give it water, that's called positive feedback. So it responds positively to something encouraging that you're giving it, a positive feedback. So if you increase rainfall, let's say in a desert, it makes everything greener, does it not? In the study of systems theory, you have to realize change is not an enemy. Now, innately, many of us are afraid of change. We dislike it. Our hearts break when we see a great fire burn off the side of a mountain, or a flood come and wash away and change everything from the way we were used to it. But I can assure you, nature is that way. It does resist change, but change is inevitable. So let's look at the left on the right-hand list, and I'll introduce you to some terminology to try to explain all of this. That when systems change, they are perturbed, they change. That is, disturbed, they will change. Equilibrium is basically a fancy way of saying balance. Now, they used to in the old days say balance of nature, but they've rejected that because that seems to be that there's a balance and then things are thrown out of balance, and that's a bad thing. In this view of the world, disasters are part of the process. So equilibrium is when things are in balance over a long time period. It's called a stable average. Disequilibrium is a future state that is uncertain. In other words, it means basically it's a fancy way of saying out of balance. On the left-hand column, we see systems fluctuating around a stable average are in what they call a steady state equilibrium. So, in other words, long-term, the land around us, the grasslands, the forests, the trees, the streams are flowing. Everything is in steady state balance. Then you have, over a long period of time, is evidence of change. And that can be seen, like, let's say, when you look at an old time photograph of a landscape, and you look up at the same landscape now and you think, this is strange. Everything has changed over the past 100 years. That's an example of dynamic equilibrium, systems in a trend of change over a long period of time. And then you have this thing that I just referred to earlier about how systems tend to resist change. We don't like change. Well, neither does nature. It resists change, and then suddenly some kind of disaster will impact it, and it goes into what they call a metastable equilibrium. That's at the lower left on the list. It's when a system lurches into a new operational state, and it's called metastable equilibrium. So it's not saying that things are a complete disaster, but that's basically a fancy way of saying there has been a disaster. So equilibrium means balance, disequilibrium means out of balance, steady state equilibrium means stable average, dynamic equilibrium is change over a long period of time that we might need an old-timey photograph to discern, a threshold is a doorway, and metastable equilibrium is a new operational state after a disaster. I'm going to illustrate what we just learned using the example of Mount St. Helens. This was a volcano that was long dormant and then suddenly became active in 1980. And as you can see in the motion picture above me, the whole side of the mountain started to slide off, and these huge explosions blew out a huge crater. Now I'm going to try to take your eyes off of that motion picture and steer them towards the lower photographs on the screen shown in green. What Mount St. Helens looked like in 1974, what it looked like in 1980 when the disaster happened, and in 2011. So first off, in 1974 you had a very lush forest around Mount St. Helens. Mount St. Helens was just a dormant volcano with snow on its top and this very thick old growth forest all around it. This was a state of steady state equilibrium. Things were in a steady state balance, we might say. Then, 1980, the eruption happens, and the forest system all around the mountain, especially on its north face, was pushed through a threshold, through a doorway, and it was suddenly disintegrated. It fell apart. The system then lurched into this metastable equilibrium, in which the first thing that life that appeared on the moonscape of gray volcanic ash was these prairie wildflowers and insects, and that comprised the initial recovery period. Then afterwards, 2011, in the photograph you can see that there's a lot of greenery forming around the volcano again. This mountain is now in a slower but changing trend of recovery called a dynamic equilibrium, where now there's grass and there's even these young trees growing and taking over the landscape. Earth systems are interconnected, and what this means is that here in New Mexico, something can be that didn't even occur here can be affected by something that happened on the other side of the planet. And that is a good example to give you. The eruption of 1991 of Mount Pinatubo in the Philippines. As a consequence, that next year, 1992, was a rather cool summer here in New Mexico. And that was because this volcano erupted and threw out an estimated 250 megatons of gas into the upper atmosphere. It threw out more pollutants, shall we say, than mankind does in years and years of active industry all over the world. As a consequence, many point to the volcano as an example of how nature can pollute more than mankind does. That, of course, is controversial to say, but the basic message in this is that Mount Pinatubo in its eruption launched a cloud that circled the globe, obscured the atmosphere, and caused a cooler summer a world away here in New Mexico. So in conclusion, let us summarize. A theory is a set of statements, principles, or ideas that rationally explain the facts and color our perception of the real world. The system is an ordered set of parts working together with some kind of driving process of energy. A systems theory, then, is how some systems all work together. They're either as an open system or a closed system. Some of them are receive positive feedback or negative feedback, and then there's changes in those systems. That's what system theory dwells upon. Then there is steady state equilibrium. It's basically a way of saying balance, steady state of balance, how something is around you. The forest with its leaves, the stream flowing, and people walking about on the landscape. Then the system can be pushed through a threshold. There can be some kind of disaster, let's say, for example. Threshold means doorway. And the system lurches into this metastable equilibrium, which is basically a time of initial recovery from some dramatic change. Long-term change over a long period of time is dynamic equilibrium. This concludes our presentation on systems theory.